Hello, I'm Michael Cormier, and I'm presenting the paper Automatic Classification of Woodcuts and Copperplate Engravings, which I wrote with Sarah Park and Lauren Beck. Our objective in this paper is to automatically distinguish woodcut illustrations from copperplate engraving illustrations. So this raises a few questions. First of all, what are these illustrations? Second, why do we want to classify them? And third, how do we actually accomplish this classification? So let's first look at a couple of examples of woodcuts and copperplates. This is a woodcut illustration on the left, and this is a copperplate illustration on the right. Now you can see that both of these depict scenes. In the woodcut illustration, you may notice that the lines are somewhat coarser. There aren't quite as many lines as there are in the copperplate illustration. Now, these differences are related to how these images are actually produced. In a woodcut, the column on the left, images are cut into fine-grained wood, often boxwood. The raised areas transfer ink to paper. The white areas in the image are produced by cutting away the wood below the surface. This results in coarser lines than the copperplates described in the column on the left, where the images are cut into, well, copper plates, hence the name. In this case, incised lines transfer ink to paper. The grooves pick up the ink and transfer it to the paper, which produces fine, precise lines and sharp edges. Now, all of these little snippets are done to the same physical scale here. So why do we want to do this classification? Well, how an illustration was produced is an important item of metadata for cataloging. An art history researcher, for example, might specifically want to look at woodcuts or specifically look at copperplates. The two classes require experience to reliably distinguish. And with large-scale scanning projects for books and artwork, producing many images that need cataloging, automating aspects of metadata collection, like this distinction between woodcut and copperplate engraving, will speed up the process, allowing more items to be made available and freeing up time for researchers and students for more creative and more engaging research projects than just distinguishing a bunch of illustrations according to how they were produced. In our data set, we use a total of 400 illustrations from 40 books, equally divided between woodcuts and copperplate engravings. The dates range from 1483 to 1739, but most of the sources are between 1500 and 1700. We rescaled all of the images to a common resolution of 600 ppi, regardless of the original scan resolution, which ensures that each pixel is the same physical size in all of the images. Now, this is important because the fineness of the lines, the sharpness of the lines, these things are important factors in distinguishing between woodcuts and copperplate engravings, and they relate to the physical scale of the lines in the image, not to a particular pixel scale in the scan. So we need to standardize them all to a common 600 ppi resolution. Furthermore, we also selected images that would show scenes rather than diagrams or portraits, because we are using a statistical approach, and the statistics of a portrait or diagram may differ from a scene. Now, at first, a convolutional neural network seems like it would be a natural approach for pretty much any classification problem. However, in our case, there are several problems with using a convolutional neural network. First of all, we want our system to be interpretable. It's intended to be used by non-experts, and a black box system may be confusing. A 400 image dataset is also likely to be too small for training most modern CNN architectures. And finally, we would like to be able to extend this to incorporate other information such as publication date or location, which may provide useful information for classifying these images. And this would be difficult to incorporate into a convolutional neural network architecture. In order to address these challenges, we took a more classical statistical machine learning approach. We use probabilistic reasoning, which we can make it relatively accessible to non-specialists. We can use these methods with a smaller data set, and the probability estimates based on appearance can be integrated with other probability estimates. For example, into a Bayesian network that accounts for the visual appearance and the publication information. Our feature selection, since we're trying to distinguish two classes based on the physical processes used to create the images, we based our feature selection on these physical processes. Now, in both cases, we use lines to create an image, but the substrates differ in their ability to reproduce many fine lines. So the use of lines has to differ based on the properties of the materials. This suggests an edge or gradient-based approach. And we use the distribution of the magnitude of gradients in the image. We took two different approaches to making use of this gradient magnitude information. In the low-level approach, we learn a distribution of gradient magnitudes for each class and classify an image by determining the probability that its gradients were drawn from each of these two single distributions for each class. This results in a very large number of samples, one sample per pixel roughly in the image, and this tends to produce unrealistic estimates of certainty in the resulting probabilities. The high-level method uses a method where we describe the shape of a distribution rather than trying to assume that all of the woodcuts share a single gradient distribution. In this case, we compute the mean, variance, skew, and kurtosis of the distribution of gradient magnitudes for each image. We learn a non-parametric joint distribution for each class using kernel density estimation on these feature vectors. This is moment-based and describes the shape rather than assuming a single distribution. It allows us to describe a family of distributions for each class. And here we can see some empirical distributions of gradient magnitudes. On the left, we see the per class gradient distribution, one for woodcuts, dotted blue lines, and one for copperplates, dashed orange lines. So you can see that there are two very distinct shapes of gradient magnitude distribution here. If we break it down with one distribution shown for each source, we can see that although we're still observing similar shapes, there's also considerable variation in these distributions within a class. So this suggests that the high-level family-based approach captures the true situation more accurately than the low-level single distribution. Our empirical distributions of the features also support this idea. We can see here that the mean, variance, skew, and kurtosis all differ in terms of the empirical distribution between the two classes, and although none of them would separate neatly with a single linear division, we can observe that each one seems able to at least partly separate them, and this suggests that these features are useful for this classification problem. So, how accurate is this? Well, one promising sign in terms of the overall utility of the method is that the overall accuracy is stable with respect to the hyperparameters. In the low-level representation, the hyperparameter is the number of bins in the histogram representation of the distribution. In the high-level method, it's the kernel width for kernel density estimation. Now, in both cases, we obtained a maximum accuracy of 88.8%. And other accuracies with different hyperparameters were only very slightly lower. The mean for the high-level method, the mean estimated probability for correctly classified examples is 0.938, and for incorrectly classified examples it was 0.770. And this difference in estimated probability is statistically significant. So the estimated probabilities do actually reflect our confidence in the results in a useful way, at least with the high-level version. Now, we would like to pursue this research further to extend and improve this method. Since we can easily support, with a probabilistic approach, non-visual evidence, we would like to incorporate things like publication information. We would also like to extend the classification to other methods of producing illustrations, to identify things like lithographs and mesotints and so on, which will make this more broadly applicable to other aspects of metadata generation. We would be able to identify other media, not just woodcuts and copperplate engravings. We also hope to extend the visual evidence used, possibly including deep learning methods to learn new features that would replace or supplement the standard gradient method. All in all, we believe that this is a very useful contribution to the problem of generating metadata for very large scanning projects that are making art and literature broadly available over the internet. Thank you.